All right, so this talk is about NoSQL in the Hadoop world. This came about a while ago. For those, let me just skip ahead next page. From my background is I sort of got stuck in the Hadoop world in 2007. End of 2007, I had a problem. I had to store all of the patterns of the world, translate them into different languages, and serve them out into the world with ads on top of that to make this worthwhile, this whole experiment. And I had to, in 2007, I had to find a way to store these documents and somehow serve them out. 2007, oh, by the way, I had no budget, so I do this on a shoestring budget, which is basically my pay. And I had to find open source software to do this. And the only way would be like use a database, Postgres or something, or MySQL, and store all these documents. And I thought that was like the sort of, I think also the beginning of the age where databases were discussed as not being the end of all wisdom. And I heard about what Google did. Google did released a paper earlier on Hadoop, like MapReduce and GFS, and Bigtable afterwards. And I thought, okay, I can purchase like 40 machines or 44 servers back then, and store them somehow in a cluster distributed. And if Google does that, then there might be a good chance I can be successful with that as well. And I was the CTO of the company, the typical DevOps, so I did everything on my own, like created scripts to deploy stuff on servers, really nerdy stuff. But it was good fun. I can tell you it wasn't a good idea to start in 2007. It was a really bad idea. It was really painful. Data loss, crashes, calls at 3 in the morning for weeks. Because my boss at that time, I was in Australia and he was in the US. And every time when he basically got up in the morning, like 8 o'clock or something, it was like 3 or so in Australia, he gave me a call, oh, the website is down, and please fix this. So not a good idea. Today, it's great. Today is great. We've come a long, long way. There's a few more things to fix, like some work in progress, but overall things are stable, we have no data loss, it's great. So overall I think the whole approach and the whole idea, the outset of Hadoop, it's a good one. Google is successful with that. They're still using Bigtable quite heavily. They have moved away from GFS, from the first incarnation of the file system, to Colossus, a different file system, which is interesting because they use Bigtable as a meta store for Colossus, and Bigtable stores that its file on Colossus. So they have a circular dependency because the file system they're driving is used to store the files that they're protecting or serving or somehow. So somehow it works. I don't know exactly how. What's really cool, I'm working on an update of that book. I wrote this book in 2011, and things have changed quite dramatically. So I'm currently working on updating this halfway through. There's an early release, and in that early release I got one of the Bigtable guys, Carter Page, to write the foreword for my book. So now we have Google committing code to HBase. They helped us clean up the API, so it's like a generic API for data use. And they're happy to talk about this. So they have user group meetups in New York City, for example, where their team sits. And as Carter was nice enough to write a foreword of how they see how HBase developed, just based on the paper, just some 7-8 pages of description of how the system works, picked up by some guy, Doug Cutting, who works for Cloudera, and implementing this in open source. And we implemented stuff in HBase that they have implemented sort of at the same time within Google without ever telling us. Some stuff we knew about, like you heard about that they're doing something like code processors, so they can now deploy code running next to their, they call them tablet servers, so that you can actually store procedures, you can call on code within where the data resides in those servers. And we did this as well as co-processors in HBase land. But we also developed something like replication and backup strategies, and they have done the same thing as well on their end. So he said when the first time we wrote this in the foreword as well, he said it was surreal because he went to like a HBase user meetup and didn't really say he was from Google and from the Bigtable team. And he heard all these people talk about HBase, and he felt like right at home because they have the same challenges. They solve them, of course. They have 1, 2, 3 more PhDs on us. But yeah, it's great to see that we're actually on similar steps. So even if you're open source and like very few, in comparison, very few developers working on HBase, we still very close to what they do, sure, at a larger scale, but it proves that if we wanted to, if we want to scale larger than what it already can do, it's possible. So that's very interesting. So I'm looking forward to what's going to happen. So this is not going to go away. For those, again, because my heart is with HBase, I can tell you that there's a lot of marketing mumbo-jumbo going around about other NoSQL solutions. In the end, I'm always saying it's physics, right? It's all physics. If they tell you they can save the world, they're lying, right? It's just flat out lying. If they say they're 100 times or 1,000 times faster than HBase, they're lying. Right? So I'm just telling you that it makes no sense to claim anything. Show some graph which you faked yourself, basically. It's like, because the way you tweak the test is like showing like the absolute worst point of the misconfigured competitor to your absolutely perfectly configured own product, stuff like that. I'm not really as, I mean, you can see I'm quite passionate about this, but I'm not really that worried anymore that much. In the past I was more worried and I was more like, why don't we do anything about that? It's just, I think time will tell. Even if they claim that they can do these things and you're buying into it, which is sad from my point of view, unfortunately it will reveal itself. It will show what it can do. But I'm also very pragmatic, which means if there is a tool that works better for this use case, or if they say, if I come in and talk about, in this case, HBase, and you present something to me, and it doesn't fit, I will tell you that as well. And this talk is about that, coming all the way full circle now. This talk is about today. When I started in 2007, there was only HBase and MapReduce. There was only batch and this real-time component that you can use. Same as they designed it back then. They had GFS and MapReduce and Bigtable. Now you have stuff in between. And this talk is about how did this sort of change over time? Like, what happened and what do we have today? What tools do we have? And how do we position them? Like, which is a good one? Which is a good choice? Or how do they all fit together? And I'm sort of like putting this again. I'm using obviously names that within our company are quite popular, like Impala in this case. You can actually replace a lot of these things with other solutions in that space, right? So I'm just using an exemplar term. So it's not just because they're doing something specific. We do, when we talk about Impala, you will see this in a minute, we do something specific for, say, very low latency, very fast query times, but overall, throughput and latencies, again, are just physics. So if we know what the tool can do or what the machine can do, and you should expect a certain performance of the software that runs on top of that. Don't get fooled into something that portrays or claims to run 10 times faster as the hardware underneath that you have. It doesn't make sense, right? So we just have to get this together. Unfortunately, obviously, often those who make the decision to buy something are not the ones who understand the physics and do not really understand what this cluster can do and might be lured into the wrong reasoning. But yeah, that's always like that. It won't change. As I said, it will reveal itself over time. That's what I've seen. Right, so we go through here the problem statement, which I already started, a bit of the architecture of both sides of the coin that I'm going to sort of sketch for you. The sort of one side is one architecture, and the other side is another architecture. And I will go through their sort of basic architecture, so you get a feel for what's happening under the hood. Because when we talk about physics and we talk about what happens or how fast does a system go, then understanding the sort of the innards, inner workings is really important to understand why one is a better choice over the other. And yeah, then we at the end, summarizing those, bringing this together again, so hopefully pick you all up at the very end before I have sort of like painted this bipolar picture. I will bring it all back together in the end. Please bear with me. Right, so this is like, I did this. Fantastic, isn't it? I use OmniGraph for everything I do, and this is one of my worst, I think, graphics that I sketched. But anyhow, so this the picture here is, we have two competing architectures. The problem. I call this a trove of indecision. A trove of indecision. So it's this well, a suspension bridge of some kind, where in the middle we don't know exactly what happens. On one side, you have the low latency queries, basically on the HBase side, random access to data, and what it was built for. But today, you have on the other side also those high throughput systems, like Impala as an example. I said this is one of the tools there. So hang on, I can do SQL on the Impala side and run all my queries that I used to run. Why would I still use NoSQL, right? It's NoSQL at its end. I can paint this picture. Is it the end of NoSQL? Because now you can do SQL. And what's even really bizarre, now I'm bending your mind, Impala can run on top of HBase. So Impala can be the engine that actually queries data stored in HBase. So you actually paint them on top of each other. So if I can do SQL or NoSQL, is it basically the bee's knees, the silver bullet? Is it the end of all questions? Of course it's not, otherwise you wouldn't have the piranhas there. I can't see them, but yeah, there's power in the middle. Right, so where does a use case fit? You are basically looking at this from, all right, I have a use case, I have some problems to solve. How do I put this? Do I put this towards the sort of like high throughput side SQL, so I can query this with standard SQL? Or do I rather store this in NoSQL and can actually do something on NoSQL side, but maybe with SQL on top, or just a native API? That is the big question, right? So there were a few choices in the past, so I skipped this now, because I already mentioned this in the intro. 2007, there weren't too many choices. Even NoSQL, there was no choice. I only had to choose really HBase as a newer breed of NoSQL. NoSQL is a term like cloud or any other of these buzzwords. Because I mean, after this NoSQL was coined, all the other older NoSQL databases came along, like GTM or Berkeley DB. They all said, well, we also NoSQL, right? Because you can't have an SQL engine on top of us. Well, we can, but we are just an engine basically, not with having no query language. So we also NoSQL, right? So, but back then I didn't really look at those. I said, I want to do something new, and what Google does has to work. So you either use something open sourcey, custom solution, or Hadoop. So today you have all of these two choices. You can do. NoSQL has I don't know, every week a new one comes out in the sort of SQL space on top of Hadoop. Every week or every other week it feels like a new solution comes out. Which is the real? What's the answer here? And again, I think you can really put them into these two corners. Yes, there is something in the middle, but that middle ground hasn't been explored yet that well. So you either have this high throughput side or you have the random access side, and we're going to look at both. Right. So which should you use for which use case? Let's first look at the underlying architecture. Let's start with Impala. This is an example. Impala is an engine. We will talk about Parquet as well in a second. Parquet is the file system underneath, and that can be used by any other tool as well. So this is just exemplary, as I said, for one of the engines. But of course, I mean, it's a really good choice. I have to say this. The changes, we're going away from just batch or random access, right? So we have two choices now. You had two choices in the past. You have more choices today. In the past, you would do something like, yes, SQL, you can use this. You can run this basically on Hadoop. And what really happened with Hive back in the days is it would just take your SQL, transform this into a MapReduce job, and run this on your cluster as a MapReduce job. So the performance of the job was that of the MapReduce cluster, which inherently is a batch system, which means you're spinning up Java processes, and that will just take time to sort of coordinate, starting up jobs, running the query, and shutting back down. The minimum sort of runtime of a MapReduce job is half a minute. By the time it's all scheduled, ramped up, ramped down. And if you then query something that you would expect a database does in half a second or even less, you don't want to wait 30 seconds for that. Because a BI dashboard that just sort of like fires off a random amount of SQL queries to drive the different dashboard items. If every of these little queries takes like half a minute, the whole dashboard takes like 30 minutes to build, and you just really walked away and quit your job. Or you try to find a job. You probably would buy today you would probably buy an in-memory high-performance SQL database. There are many of them high. Right. So you want to speed things up, that's the problem. There are efforts going on, and you know there's probably with Hive as well to speed up Hive. Tails is one example. Our friends at Hortonworks, they do this. They work on trying to rip out MapReduce, which is now anyways an application running on top of Yarn. So Yarn is now the framework, and MapReduce is just an application. So why not run another application, Tails, that then drives, because it runs constantly, it drives Hive, taking immediately away the startup cost. Right? So that's basically the idea. Or you can basically do other things on that end. There's many sort of choices to speed Hive up. There's efforts going on for those who know Hadoop already well. There's Spark. Spark is sort of hyped as the next silver bullet for everything else in Hadoop. Again, I'm a bit, I might have the undertone. I don't think you shouldn't bet on any of the components for 100% to stay, because Hadoop for me, Hadoop is an ideology. It's about data first. Data in the central part of your system, and you ship applications to that data. How this data is stored, how the application is shipped, what framework this application runs in is all replaceable. So never say Hadoop is dead, or you could say MapReduce is dead. That was like a news a while ago, because Google said we don't do MapReduce anymore. So everyone thought Hadoop is dead, because sort of they make that next logical step, which is ridiculous, because as I said, Hadoop is an idea, MapReduce is a component. Throw it out, bring Spark in, that's fine. In the future, a couple of years' time, Spark might be replaced by something else. So just saying HBase might go away and another file system comes up. That's independent of the idea. Right? And this is also independent of the physics. Right? So everything I'm saying is really trying to hone you into the idea of don't really buy into names, think about the overall larger picture of things. And then you have a good foundation to decide which way you want to go. Right? So yes, there are other ways to do this. Like that Spark is one, so you can run something in memory. You can sort of like keep things in memory. You can preload them if you want to, memory map them in as well, and you can constantly run, and you don't have to load anything, which buys you immediate performance boosts because you don't have to have any wrap-up time. Same is what Impala does, and a bit more on top of that. Google also realized this. If you follow just a paper trail of what Google did, one of the papers they brought out was Dremel, if you remember that one. So Dremel was about querying, I don't know, it says here, 1 trillion rows in seconds. Everyone was like, mind blown. Right? So like, how can they do this? How can they query 1 trillion rows in a second, a couple of seconds? This is amazing. Well, the reason is they don't touch all of the data that's behind that data set, right? Obviously, the same idea that you know from the speed up of columnar databases, where you store tables in columns, and you can now query over those columns. You can drop all the other columns you don't need. That's the same idea. You can do, because now 1 trillion rows is not 1 trillion times, I don't know, 100 columns. Now it's 1 trillion rows of one column in one query. So it's only with 100 columns, you only query one column, it's 100th of the data that you have to scan. And if you bring this further down and optimize the layout, you skip ranges, all of a sudden you can scan 1 trillion rows, but you're not touching 1 trillion rows, right? Again, physics. Can't fool physics. Right, so this basically came out, and they had a columnar storage layout. This is something that we re-implemented again. Pretty much everything they sort of release, you will find somewhere in Hadoop, someone's picking it up and saying, oh, that's a good idea, let's do this as well. And it's the same, and you will see how their file format is the foundation for K. Right? So what are the goals for our Impala? Just as this is an example of an engine. It's very similar in their overall goals, so we can use this as well as an example. Have SQL on top of data stored in a cluster. SQL is something that a lot of people know. We always say MapReduce, basically no one knows, only a handful of people know. Scala even fewer people. But so MapReduce in Java, you find a few people that can do this. SQL, you find many people who can do that. But if you could do search, for example, pretty much everyone can search. Even my mom can search on the internet. So we have this sort of steps of accessibility. If you make it searchable, everyone can search it. If you make it SQL, it's much better than all the other choices. So Facebook did this, also saw this early on, and did Hive. It's the same effort. And here, basically, we have a similar effort. We store data in a large cluster. We want to query this with a DSL that is very much in use, broadly in use, so we don't have to retrain people. Right? So SQL was added on top of Hadoop, and you can just write SQL queries. It's typically for specific workloads, so analytical and transactional. Transactional is one of those things that is not really there yet on the Hadoop side of things, right? So transactional means you can update data. That's something that we don't have yet, but it's an overall goal of an SQL engine, so we have to cover this sooner or later. We want to have queries that run in milliseconds, 2 hours, like running like longer jobs on top of that as well. That should work. And it should somehow be on the cluster. So again, data first, the cluster has the data, and we ship all of the queries, all of the parts of the queries down to where the data resides and query it there, so we don't have to ship data. Shipping data at scale, bad idea. No one wants to do that. Again, physics, as soon as you go from memory to disks, and from disk you go to network, and so on and so forth, and you go then to maybe to a link between 2 data centers, you get these, like, I don't know, magnitudes of drop-offs of performance. So try to have the data stay where it resides, and ship the code over. So you're writing a query, and the query gets distributed over the cluster. It's the only way to do this with this sort of performance. So you have the daemons running on the same nodes as the storage. We want to make sure that we can write or read data in file formats that are not specific to that engine. It's very important. We are in the open source space. If you were not in open source space, you would do something like Replum, for example, and you would rewrite all of the data into their database format, and then you can query that maybe fast on the end. But only the engine can read that data, because you do not have a description of how the file format looks like. That might change now, since Impala now open source, so things are changing there as well. But just saying, if you want to land data, you want to land it in a format, every other tool in your tool chain can read as well. That's important. And we will look into the physical layout in a second. It's written in C++. This is our part now. There's others are written in Java. This is written in C++ because we can then optimize the query using LLVM. So we translate the query into intermediate code, run a code optimizer on top of that query. We can do like inline loops and things like this. We can optimize the query and then read the data directly from storage. That's important. No MapReduce involved. Like, this is, again, a typical thing. We don't want to have spin-up times, shutdown times. We want to just run right away. Right. And, of course, we want to make sure that Hive and going from Hive to Impala is the same thing. Right. Just for like feature sets, we have HiveQL as the query language, so you can actually write all of the queries that you can write in Hive, also on Impala side. Of course, there are some extensions on the Hive side. For example, some of the like serializers. There's a way of treating data arbitrarily. We don't have support for that yet. But as I said, for the majority of queries, we should be able to go back and forth with minor changes. And then, as I said, we can query data directly in HDFS or in HBase. Right? How does it work? I mean, it tries to reuse not just the file formats, it also tries to reuse the schemas. So Hive has already a schema store, so why reinvent the wheel? We use Hive's meta store to store all the schemas. You can use ODBC to talk to it, so it's very much fits nicely into all of that concept of other systems on top of Hadoop. The queries, as I mentioned, are distributed now across all of the machines, and I have a few slides on this one in a second. And then there's another thing that MapReduce did not really consider, for good reason. Whenever you run multiple MapReduce jobs, one after the other, and even the stages between MapReduce jobs, there are times where the MapReduce system says, I don't know how much data you sent me, so I'm going to persist this on disk in between. It creates always a temporary storage where it lands the data, the next stage reads it. Especially between MapReduce jobs, you persist the data, the next job picks the data, persists the data, picks the data. So if you run an SQL query, often you can't run this SQL query in a single MapReduce job. If you have lots of joins, you have to like read from multiple locations and do these joins depending on how they are joined from multiple sources, and that means multiple MapReduce jobs. And every of these MapReduce jobs reads, merges, writes, reads, merges, writes, and all of that costs you even further time. Not just the spin-up time, it also costs you time to write to disk and read from disk. And of course, in a higher performance in-memory structure, you don't want to do this, so here we want to do process-to-process communication, so we stream data from one node to the other in memory. And again, this is not rocket science, as all of the database that you know do this as well. It's just, again, we want to, it's physics, right? So if you hit disk, it's very slow, if you stay in memory, it's faster. Same thing here. And the other features I sort of skip. The other thing is, and this is where we get now to back to my trough of indecision. One of the performance goals of these engines is, in this case, is to be as fast as possible. Again, physics, we want to really use the disks to their full performance. So if we have disks, and we sort of like ballpark these days, saying 100 megabytes per second per disk, we want to make sure that the engine can really saturate those disks. So as few as any conversion or anything that you have to do to slow down that performance should be possible. That is one of the performance goals, to be really fast. You will see how this basically, and I sort of like jump the gun a little, you will see this on the HBase side later on, keep this in mind, that we trade this off for other features on the HBase side. So here's one of the features that on the one side of that bridge is really important to us, while on the other side we can't really get there. We will see this in a second. And I mentioned multiple MapReduce traces. You can see the speedups there 45 times, and then if it stays, most of it fits in memory, you get like 90 times speed up. And this is not because we are like the greatest people in the world. It's just because you're skipping unnecessary I/O, unnecessary speed up times or spin up times. It's just low-hanging fruit performance gains just by converting the architecture to something more reasonable. And again, as I said, MapReduce did this for a reason. MapReduce was very early on, and it did this because back then the design was just batch-oriented. So if you don't do batch-oriented anymore, you want to do something near real-time to real-time, you have to change this. And this is exactly what happened. Right, so let's have a look really quick into how this looks like architecture-wise, so that you see how like this is being resolved. We have two daemons. One is the Impala daemon that runs on every node where the data resides. So every data node in Hadoop would have an Impala daemon next to it. And we have a state store daemon which holds the state, which then sort of, for example, caches the schemas and other things, knows which nodes are running. It's like a master that controls or that keeps state of this, what's called state store, of course. It keeps the state of the system, right? And we only need one of those, or few for failover, but they store the state of the cluster. Right, so the way it looks like is now that every Impala daemon, these are the three physical nodes at the bottom. So these are the physical nodes. And basically I have HDFS underneath, or maybe a HBase region server, or both. So if you have a very dense cluster with everything loaded on the same node, come on in. There's pizza too. Oh, there's pizza. Every of these physical nodes sits on top of where the storage resides. And then they have some components, and every now and then they pull the state daemon just to get updates of what the current state of the land is. So that's basically what it does automatically. Right. Now here comes the query, and the query is on the left-hand side up top. Now we have a query coming in through ODBC, and one of the daemons, I think it goes around Robin or so, one of the daemons reacts to that query and says, okay, give me the query, what do you want? So that one then hands over that query through ODBC to a query planner, which then computes based on the query, where is the data really, like which node has that data, and then takes that query and uses the coordinator to send all of these queries to the nodes that hold the data. And in this case, say all three nodes are involved. So part of that query goes to node 1, part of it goes to node 2, and the other part of that query goes to node 3. So they all get their subset that they have to query, the data that they hold locally, and they go and spin the disks. So in this case, we see here that they're either reading here from HDFS there as well. Here's an example. There's maybe a join through from a HDFS file with a HBase table, and in this case it reads here from HBase, and the other one's from HDFS. Streams that information back to the coordinator, which merges all of that magically, and then goes back through ODBC out to the caller. All of that, as all of the other bits and pieces are flying through the Ethernet. So this is basically how this works on a high level, fairly straightforward. I mean, there's many other systems that follow a similar approach. Nothing of that is really special of sorts. Where, just to give you like, I don't want to miss the point of saying something about Impala. The edge that we have in Impala over all the other systems that I believe we have is that the optimization part. We really are optimized for SQL data reading, while other engines often try to be a system that can do many things. TASE, for example, is built as a generic DAG, direct acyclic graph processing engine, so you can run other systems on top of it as well. And having lots and lots of things pluggable is, when you look at the top percentile, basically the best performance part, I think we have an edge there because we're just more concentrated on this part over being more generic. This is the only difference. So I think we are having an edge on that. And the other thing, when we say you ever have to evaluate these systems, like Impala versus, I don't know, the other things that I already mentioned, make sure that you test this in a highly concurrent access. I think we also have an edge because we are really built for lots and lots of concurrent access to that to the queries, while other systems in a single query might be very close performance-wise. But if you run hundreds of parallel computing or hundreds of parallel queries against these engines, you will see how they differ. So make sure you test them under production conditions. So that's the only advice I can give you. Yes?
Are all operators in a query plan running in the query exec engine, or just some running in the query coordinator?
No, that's always passed on to the query exec engine. The coordinator basically is just coordinating the flow of, so it takes apart the query plan and ships it over to the executors. They are the ones who actually read then from HLS. They have the drivers, so to speak.
But I guess they are also sending data to each other.
Yes. Yeah, exactly. It streams back here, for example, streams back to the coordinator, which merges all of that data locally and remotely, and then ships it over to the caller. No moving parts, basically, or everything streaming-wise. Now, this is one part of the coin, right? The engine, to be able to scan really fast and as fast as a disk can spin. How can you do this? How can you do this even faster? The only way to make this faster, again, physics, is reducing the complexity. We're taking something out. In this case, the only way, and you sort of see this as none of that is really rocket science that we talk about. You have seen this with the columnar databases, the analytical databases that you saw coming into fashion a few years ago. They did the one thing that they said, okay, now we're doing row-based queries. We can do so much per throughput on disk. Shorter data run faster because disks have also increased in their performance and throughput. But how can we further improve the performance? And the only way to do this is to not look at data that you don't need for a certain query. And that is what Parquet does. So Parquet is really built for analytical workloads. And because these analytical workloads often, you have a wide table. You have sometimes, I don't know, thousands or 1,000 columns in a data set. Right? Maybe you have even a structured data set, a leveled data set, like it's multi-levels. So where you have one column being a complex type, which has further fields inside. So this is something that gets on a database, gets really hairy really quickly. But say just for us to get started, it's just if you have 1,000 columns flat next to each other, and you need for this query only 10 or 100, why look at the other 900 or the other 990, whatever it is? That's exactly what this does. Typically, these queries do not need to have all of that data. They're very selective. So let's have a file format or have a layout that favors this kind of query. It's open source, so everyone can use this. It's developed in cooperation with a couple of companies. Twitter was one, Cloudera was also involved, so but it's open source, as I said, and again, it's open source. There are competing formats, so Parquet is not the only one out there. There's also others, ORC, for example, and they're all like fights or whatever. So it's not good for you. You guys have to decide which one to use. Sorry about that, but that's the way it goes in open source, I guess. So let's have a look at how this works. Twitter data. This is from a presentation of theirs about Parquet, I would say, probably already 2 years ago, a year and a half, 2 years about, yeah. So the data is just it's not current, but you look at what they do there, how many they get. 500 million and more tweets per day. Sounds a lot. 500 million plus tweets a day. Again, I challenge you whenever you hear numbers to do the math, because if you multiply 500 million tweets by 140 maximum size, and if you take the average size of a tweet and then do the math, it's only a few gigabytes. So it's not really like this is like petabytes of data every day, right? So, but it would challenge a database. If you were to insert like 500 million rows into a database with all that B-tree orientation, or they have like indexes they have to maintain, it makes it challenging. This is the idea here. You don't have to think about how many rows you have. Just insert them. That's the idea. Data first. Insert everything you want, and then we figure out querying afterwards. It's an approach, right? You can see they say 100 terabytes plus of compressed data, which is not just tweets. Also, they derive lots of information from the tweets, and they also get a lot of metrics from that data. So there's a lot of metrics that come in from every server that runs. So they produce data out of many different sources. So this is all like a combined amount of data that they have to store. And yeah, you can see they have an analytical infrastructure, several 1,000 node Hadoop clusters, so it's a decent size. Log collection pipelines, so that everything that comes in gets logged, and they're processing afterwards. Now, if you look at this schema here, this is more of a real-world schema. So if I said 1,000 columns, that sounds great, but this is more what they wanted. So what they wanted is a nested structure. So they have a structure where this is a log event, and out of that log event, one of the fields here, for example, log base, is another structure underneath. So they have a multi-structured way of laying out that data, which makes sense, because why would you just press this all into like a relational schema if you don't have to? You're not a database, so store this in a complex nested structure. Use an Avro or other format to store that data in a proper record, because then at query time you have much more control over what sits where, what you want to query. You don't have to like keep these complex flat structures around, right? So here they have 87 columns, up to 7 level deep of nesting. 7 levels. There's one level here, and there are many more of those deeply nested, right? So they wanted to have somehow, again, this is sort of, you can see how this matches with what I just said earlier. They wanted to have a state-of-the-art columnar storage across Hadoop platforms. So they want to have multiple systems querying the same data. Right, this sounds very much what we already mentioned so far. There's somehow a file system that covers that as well, open source, exchangeable. Okay, let's see how they did it. Use Hadoop because they know Hadoop well, that works well for other things, so let's run this on top of that one, why not? And take advantage of this column-based storage, so that you can do pretty well, like you can do highly selective queries very efficiently. And as I said, it should be exchangeable across frameworks. Why? Again, I mentioned this. It limits the I/O. It's physics. You only look at data that you need. It saves space because you can compress much better. We'll see this in a second. And you compress better because you have a type-specific encoding. If you have all of the age and all of the int fields next to each other, there might be much more repetition in those fields, and you can compress much better prefix compression and other things than if it's in a row-oriented format where the age or the date is basically spaced apart by other random length or random fields, right? Some strings and some other blobs over there. And this layout also enables to do vectorized execution engines where you do these operations where you fetch multiple data in one call, right? You can process multiple data in one call. That's very nice. So you can tell the I/O, fetch me that log, and you do with one I/O, you get that data of a couple of fields, and you can process this in one operation. The CPUs that we have support this sort of thing. here's the difference. On the top you see the row-based layout, where you have ABC as the columns and the values, and they're stored like this, ABC1 of row 1, ABC of row 2, and so on and so forth. And here you have it next to each other. So no, as no rocket science, nice colors, but very easy to read. Right? We store everything next to each other. And that's exactly what Parquet does. So Parquet is again, as I said, is based on what Dremel did. They had column.io, that's what it was called. And it's common, it's language independent, so you can run this on multiple systems, open source, specified formally, and there are different implementations for Java and C++. So you can actually read from multiple systems. Not just Hadoop, you can also read it from outside of Hadoop. Again, as I mentioned, this column.io is the founding father of the offspring, sort of the parent of this one. And there was a paper that came out, and it was modeled after that idea. Why not? Schema is defined in a familiar format. In this case, it's the ad row or JSON or something. You can basically define that format. You have nested data structures you can put in. Every cell is encoded, and here comes a bit of the internals as a triplet. It has a repetition level, definition level, and a value. The reason to do that is that we can actually omit missing fields in a structure. Imagine you store a row, and one row has all of the fields filled in, and the next row doesn't. If you then fold this basically upside down, you store the columns sequentially. You would have to put gaps in between the columns where there is no value. And to avoid this, there is a way of encoding this with very small bits, like 1, 2, or 3 bits. To say this value came from the current record or from the next one, and so on and so forth. So you can further optimize the I/O by reducing and 3D condensing a data structure which might be sparse into just what you need on disk with an encoding on top of that. It's really efficient. And yeah, so the complexity of that one is really driven by the depth of the schema. So 7 level deep only needs a few bits, for example, to encode. Very efficient. So as I said, this protocol, not average. In this case, it's protocol buffers. So there's a description file where you specify how the schema looks like. I'll show you in the next slide. You can do basic operations. Some operations are omitted, like maps or lists, but there's other ways to get around that. There's a workaround on this one. So I kept it deliberately very simple. Didn't want to have all the complexity of a serialization format, right? And then the root is called the message, and then you have these different field types with a specific number of repetitions, and it just as you don't have to remember all of that. This is how it looks like in as an example. So there's a message address book, it's a record address book. Has a required string called owner, required string called repeated numbers of flow numbers. So 0 or more. This is why it's repeated, but it's not required. Has a repeated group context, so you can have 0 or more group context, which consists of at least a name, because it's required, and an optional phone number. So it makes sense. An address book without a name and a telephone number, I think you can do this in Microsoft, I don't know, Outlook or so, you can probably create this one of those records, but it makes no sense, right, to create an entry that has no details, right? Just saying that this makes sense to build that way. The way it's laid out on disk is in the file format is then considered is grouped again the rows, so that the rows are then unfolded into columns, are grouped together, and it's a couple of rows together, and in that group, it is row grouped together, so you have a chunk of rows. We then orient them basically by column, so you have these column chunks inside, and inside we have a page to make I/O even faster, so we don't have to, if we know, for example, that a certain page does not hold a certain, let's say, a range of values, we can skip the entire page and further speed up performance, because we don't have to scan all of, even the columns that we select, we can skip if we know exactly, if we know enough, have enough information in the where clause to make sure that we can skip more information. This is how it looks like. Again, as I don't worry about all the details. There's a test afterwards who wants to win, has to basically remember this and paint this basically out of memory. Just kidding. So this is basically how it looks like. So it's like groups, and inside the groups you have like these groups, columns, page, and then sort of like the information is in there laid out that way. As I said, this is also work in progress. Things are being already added to this stage. This is a slightly older slide deck. So this changed as well.